In this brief presentation, I'll talk about how you can simulate a CMUT or an array of CMUT in COMSOL using an axisymmetric model. So by axisymmetric, it means you don't have to model the entire 2D geometry. The symmetry is assumed in all the domains, for example, pressure acoustics or solid mechanics, electrostatics, whichever you use. So COMSOL knows that a part of the model that is being simulated is symmetric. Okay, you don't have to include the entire geometry. So there are two competing models that are relevant to CMUTs or any other transducers like PMUTs or piezo's. So on the figure in the left, you have a single cell model in which you have the radiation conditions are being emulated by a quarter circle or a spherical, you can say, absorbing or perfect matching layer absorbing boundary, which is there to ensure that you don't have any reflections in your wave solutions which are emanating from a vibrating membrane. Okay. But this model is limited to a single cell. If you want to simulate a 1D array, for example, having a certain membrane pitch and curves, then you need to introduce a symmetry conditions in a waveguide model. So in part B, we have a waveguide model that is suitable for finite element analysis of CMUTs having more than one cell. So if the symmetry is simple or if you have a few cells, then the model, this model will work fine, but it becomes very difficult, for example, to simulate a 1D array having 120 CMUT elements, for example. So you need to include the effect of neighboring cells. So the symmetry condition is different from the axial symmetry. You must note that, and it includes the effects of the other cells. So the fields and the waves which emanate from the vibrating plate, they become very they become the wavefronts are, since the wavefronts are in the same plane as the membrane, so they become they're not spherical, they are plane waves. Okay, but for frequencies, high frequencies, or let's say below a certain cutoff, you have the plane wave, but frequencies higher than the cutoff, you still have some spherical propagation in this model. This is the waveguide model, which is very suitable for simulating a large number of CMUT arrays. Okay, I'll put the reference in the section below, and you can have, if you're interested, you can read more about advanced and capacitive micromachine ultrasonic transducers and how they're simulated in finite element softwares like COMSOL. So just to show you the how these models can be used for evaluating their, for example, impedance, electrical impedance of CMUTs. I have, let me share some, yeah, let me share a simple model over here. You see you have a front membrane which is made of LPCVD material, and then you have a PECVD passivations around the cavity. The top and the bottom electrodes are made of aluminum, and the lateral and the vertical dimensions are given as such. So a short version of it, if I can give, is that you have the front membrane, which is 2 micrometer thick, and then you have about 6 micrometer thick passivation, that is PECVD silicon nitride, right? LPCVD, this is LPCVD silicon nitride, this is PECVD silicon nitride. So the entire stack is about 10 microns if you do not include the substrate, which is made of an epoxy, that's Epotech 301. So if you exclude that, the total layer is about 10 microns. It's about 8 microns. Yeah. Okay. Now, if you define these material and geometrical parameters in the 2D axisymmetric COMSOL model like this, and evaluate the total surface acoustic pressure, you have something like this. So you have a series of relaxed pressure regions and compressed pressure regions. And you can see that this is for a single cell, and this does not include the epoxy substrate. So the frequency is about 7 megahertz. That's the real part. And the front medium that is loading the membrane is water. Okay. And the reactive part is, you can see it's all negative. It shows onto the structure of CMUT. It's capacitive because there's a cavity between two electrodes. But it's a nonlinear capacitor. You have a nonlinear profile, and that's a source of nonlinearity besides the transduction force, which is proportional to the volt squares in CMUTs. So what is being simulated here is that if you apply a time-varying harmonic signal between the top electrode and the bottom electrode, the top electrode starts vibrating in response to the time-varying harmonic signal, and it might generate nonlinear stresses into the back passivation, which is about 4 microns. And if you consider this, the frequency, which comes out as a function of the geometrical and the material properties we are giving in COMSOL, the 7 megahertz implies that your wavelength in water is about, it's a little more than 0.2 mm. And but if you consider higher longitudinal speeds of sound in silicon nitride passivations, about 8,000, then this wavelength is about 1.2 mm if you have dispersive waves, because PCVD membrane is PCVD, and the LPCVD membrane, which is vibrating, is counterbalanced by the passivation, right? And the part of these vibrations, they may couple into the backing, and if it's not a solid backing, it's a very it's a very thin backing, but it's there, yeah. So there will be, in response to the vibration, the counter vibration are going to include the tensile stresses. So because of that, it might act as a bilateral CMUT. So this becomes, the back passivation becomes a second ultrasound medium, just like you have at the front, that's the water. You might have the second ultrasound medium over here. So that can be in COMSOL if you include the damping losses in solid mechanics and select the PCVD, and you assume that the PCVD passivation is homogeneous media, and you can change the isotropic losses. You can do it in FAMs as just for simulations, and you will see that you will start looking at the energy losses in the impedance measurements. So I've done so, and here is the result. So the blue one is without damping, what we have seen over here. There is no pressure acoustics enabled in the backing, and no isotropic losses given in the backing material. But if you go on increasing those isotropic losses, for example, this 2 is a huge loss that can kill the resonance of 7 megahertz, and it sort of introduces those dropping baselines. So the real part is dropping with frequency. This is because the radiation resistance in the backing is very different as compared to what you have at the front. And if you consider this case is of a finite substrate thickness, it's not a solid substrate. It's a very thin substrate compared to the wavelength. So the wavelength could be 1.2 mm if you consider a silicon nitride, PCVD silicon nitride, and that is about 4,500 nanometers thick, which is about 4.5 microns. 4.5 microns is nothing compared to 1.2 mm of wavelength, given the frequency of the architecture of the transducer. So if you start giving these kind of losses, the structural losses in the PCVD passivation, and you go on increasing those losses, you see this effect, that is the Q is becoming much dampened, and you tend to introduce sort of Moore's loss in the model. So there's more wide bandwidth response, but the frequency response is like the real part. The real part is dropping. It's decreasing with increasing frequency. Okay. The imaginary part is capacitive throughout, and there's not much of the dependence on the backing loss on the capacitive part. Yeah. So, but this is with isotropic electrical loss in PCVD passivation. Okay. And the same thing happens if you consider if you introduce the symmetry conditions, periodic boundary conditions for emulating 1D array. And these are now 120 elements. Now we have both the real part and the imaginary parts, capacitive and the real part. But this is again um, without any pressure acoustics enabled or any structural losses introduced into the isotropic homogeneous passivation layers. So you see there's no pressure at the total surface coastal pressure, just like in a perfect matching layer. There is no pressure. It's all gray in the uh, in the PCVD silicon nitride passivation. Okay, so in the backing there is no loss. But if you tend to increase the loss like we did for single element, the same trend occurs. Okay, the bandwidth is high and the bandwidth becomes more if the loss is more that is expected, and those dropping frequency characteristics, they become more and more apparent. So this is for 1D array. So you see a large impedance. It's about 2 mega ohms, and but this is for the frequencies. But if you consider DC, but at low frequencies, it's not that much. It's about 800 kilos ohms, 1D capacitances. Okay, yeah. So this is for the single cell, and this is for the 1D array. But the same trend occurs if you include the losses in the backing, and this backing in this case is a PCVD silicon nitride membrane. It's not a membrane. I'm saying membrane. It's a back passivation film which is of thickness of 4.5 microns, and which might has the tensile stresses due to the vibrating membrane, and this is due to the dispersive elastic waves in the bonded solid media, and that acts as a second ultrasound medium, which may reduce the measured quality factor. We don't have the measurement. This is just an idea. So it might reduce the measured quality factor and increase the bandwidth due to the introduced loss into the CMUT medium, into the CMUTs transducers. Okay, and that's all. Thank you for listening and have a good time.